In the middle of the open sea, bridge supports descend dozens of meters into the depths, where the pressure of the water can crush metal, and the seabed is constantly shifting. It may seem like these structures are built using cranes and concrete, just like ordinary buildings on land. But the truth is, everything happens completely differently. In fact, engineers first create a dry zone inside the sea, completely isolated from the water. Imagine this. A giant metal cylinder slowly sinks into the water. Inside it, the water is pumped out, exposing the seabed. Workers descend below, directly beneath ocean level. Massive pumps run without stopping for even a second. But even here, there is no safety. The ground can suddenly collapse, the pressure can shift instantly, and the entire structure can tilt within minutes. In these conditions, it's impossible to work for long, and any mistake comes at an enormous cost. In this video, we'll find out how engineers literally outsmart the ocean and build where it seems impossible. We'll show the technologies that make it possible to support entire bridges on unstable seabeds. And what happens if that protection suddenly fails? Let's go underwater and see how bridge supports are really built where there's nothing but depth and pressure. Imagine a steel chamber the size of a multi-story building. It slowly descends beneath the water in the open sea. This is a caisson, the only place on Earth where people work below the seabed, separated from the abyss by nothing but a sheet of metal. The walls of this chamber constantly vibrate under enormous stress. Outside, the ocean presses against them with enough force to crush a truck. But inside, it's completely dry. Engineers use a technical trick that seems insane. They pump air inside at such enormous pressure that it literally forces the water back out into the sea through the open bottom. You begin descending a narrow ladder. With every step, the pressure in your ears grows stronger, becoming almost unbearable. The temperature inside rises rapidly. The compressed air becomes hot and heavy. At a depth of 40 meters, it becomes incredibly dense. The smallest spark in this environment could cause an instant and violent fire. Oxygen in such concentration becomes extremely dangerous and aggressive. You enter a zone where the laws of the ordinary world no longer apply. The main enemy here is not only outside. The roar of powerful pumps on the surface drowns out every other sound. If these machines stop for even a single minute, the water level inside will begin rising rapidly. But there is another extreme. If the air pressure inside becomes even slightly higher than calculated, a blowout occurs. A massive steel cylinder weighing hundreds of tons can shoot upward like a cork from a bottle. It means the instant destruction of the entire structure. Engineers are forced to balance on the edge every second, maintaining equilibrium between two elements. At the very bottom, workers drill through silt and rock. They prepare the foundation site for the future bridge support. Visibility is almost zero. The light from powerful floodlights disappears into a thick fog of water dust and mud. At any moment, the ground beneath their feet can suddenly give way. If the caisson tilts by even 3 or 4 degrees, it can become permanently jammed in the seabed. Correcting such a mistake at that depth is nearly impossible. Every second spent here is a risk that can never be fully calculated. When the first builders began emerging from these steel traps into the fresh air, something truly terrifying started happening. Strong men suddenly lost consciousness right on the decks of ships. People felt sudden weakness spreading through their bodies, and their condition rapidly worsened. Doctors could only shrug helplessly. People called it the curse of the depths. No one understood why the ocean drained the strength even from those who managed to return from below unharmed. This mysterious illness nearly destroyed the construction of the most famous bridge of its time. And the truth behind it turned out to be far harsher than any legend about sea monsters. In the 1870s, during the construction of the famous Brooklyn Bridge, workers began facing something beyond understanding. They spent entire shifts at great depths, performing the exhausting work of digging through the seabed. Everything stayed on schedule until workers started leaving the site en masse because of a strange illness. It turned out that the rapid transition from the dense atmosphere inside the caisson to normal air triggered processes inside the human body that science at the time could not explain. A project worth millions of dollars was suddenly on the verge of collapse because no one understood how to safely bring a person back from the seabed to the surface. The chief engineer of the project, Washington Roebling, suffered more than anyone from this unknown danger. He spent far more time underwater than ordinary workers, personally supervising the installation of every section of the foundation. One day, after climbing back onto the deck of a ship, he realized he could no longer take a single step. The talented engineer lost the ability to move on his own. But even in that condition, he refused to abandon his work. Roebling turned his bedroom into a command center. For hours, he stared through a powerful telescope mounted on a tripod, watching the bridge supports rise in the East River. Every technical decision passed through his strict supervision. He wrote down his instructions and sent them to the construction site through his wife, who became his only connection to the outside world. The reason behind the workers' strange condition was hidden in the behavior of gases under pressure. Inside the steel caisson, the air was so dense that it literally saturated every internal system of the human body. The problem began the moment the outside pressure dropped too quickly. Engineers realized that to protect people's health, they had to outsmart physics itself. They introduced a system of gradual decompression. Now the ascent from the depths took many long hours, during which the pressure was reduced in microscopic increments. This solution made it possible to complete the bridge and gave humanity the key to conquering the depths. The supports of the Brooklyn Bridge were eventually secured successfully to the bedrock, proving the reliability of the caisson system. But even after engineers learned how to work under pressure, nature itself struck from another direction. In Japan, builders faced a situation where a perfectly calculated support ended up out of place in a single second. The Earth's crust beneath the Akashi Kaikyo Bridge shifted at the exact moment when the structure was at its most vulnerable. This event forced scientists to completely rethink everything they knew about the strength of concrete and steel. They had to lengthen the finished bridge during construction itself, fighting against the aftermath of one of the most powerful disasters imaginable. Do you think something like this is impossible? It's shocking when gigantic steel towers 300 meters tall suddenly begin to sway. Engineers were confronted by a massive shift of nature itself. In January 1995, a devastating earthquake struck Kobe, Japan. At that very moment, construction of the longest suspension bridge in the world was in full swing across the Akashi Strait. Two colossal towers had already been firmly secured to the seabed, and the first guide cables had been stretched between them. The force of the disaster was so immense that a tectonic fault passed directly between the foundations of the structure. When everything finally became still, the engineers were stunned by what they saw. The bridge towers had moved apart from each other by nearly 1 meter. The situation seemed catastrophic because projects of this scale require precision down to the millimeter. All the prepared roadway sections and the main supporting cables could no longer reach their intended positions. The engineers faced a choice: admit defeat and dismantle the giant towers, or attempt to finish the bridge. Specialists carried out emergency calculations and discovered that the reserve strength of the foundations had allowed them to withstand the shifting earth plates without a single crack. But now, they had to delicately redesign the entire structure without stopping construction for even a single day. To compensate for the sudden widening of the span, the designers had to change the configuration of the suspension systems on the fly. Laser rangefinders were constantly used across the site to make sure the towers had not started tilting under the weight of the altered load. In the end, the central span of the Akashi Kaikyo Bridge became longer, and the structure itself turned into the most flexible and resilient object ever created by humans in an earthquake-prone zone. This case proved that a properly designed support can survive even the movement of continents if the correct principles of energy distribution are built into it. However, even the strongest concrete and the most flexible steel are powerless if there is no solid foundation beneath the support. In some parts of the world, engineers are forced to build bridges where the seabed consists of a massive layer of liquid silt, almost like thick jelly. In such conditions, it is impossible to use caissons or ordinary foundation blocks. To keep the structure from slowly sinking into the abyss, builders must harness the force of gigantic hammers. It is there, in the struggle against unstable mud, that the tallest and most invisible parts of bridges are born, extending deeper into the earth than any skyscraper rises into the sky. Do you think it's impossible to install a multi-ton pile in a place where there is nothing beneath the water except liquid mud? Placing a normal support on such a surface is like trying to build a structure on top of thick soup. To anchor a bridge in these conditions, engineers use colossal steel columns. These are gigantic, hollow pipes designed to pierce completely through the layer of silt. Every 30 seconds, a diesel hammer the size of a 5-story building delivers an impact so powerful that marine life can feel the vibration from dozens of kilometers away. It is the only way to force the metal to bite into the abyss, carving a path toward stable, solid ground. The greatest danger here lies in the unpredictability of the earth beneath. There have been cases when, after another udar, a pile simply vanished from sight, disappearing underwater in a fraction of a second. That means a void or a gas pocket was hidden beneath the layer of mud. At that moment, the engineers on the barge see a sudden spike on their monitors. Resistance has dropped to zero. If the process is not stopped in time, the multi-million-dollar structure will be lost forever. But when the steel finally hits solid bedrock, the sound of the construction site changes instantly. Instead of heavy impacts, a sharp ringing sound echoes above the water, almost like a bell. This is known as the refusal point. The pile has reached its limit and will not move another millimeter. It is now part of the planet itself. But what happens in places where the bedrock lies too deep, beyond the reach of even the longest pile? In these locations, engineers use the phenomenal effect of side friction. Instead of driving a single pile, they install an entire cluster of dozens of them. The pressure of the surrounding soil becomes so immense that the silt tightly grips the steel walls of the pipes. The support does not stand on solid ground. It is literally held in place by millions of tons of sand and clay, preventing it from shifting even a millimeter. The total contact area between the metal and the earth beneath just one support can exceed the size of several football fields. It is an invisible engineering force hidden deep beneath the water. Once this steel foundation framework is complete, its upper sections are filled with ultra-strong concrete, creating a platform for the main bridge tower. It may seem that the battle against the elements ends here, but this is exactly where aggressive chemistry enters the game. Salty ocean water is a corrosive solution that causes modern steel to rust and concrete to crack and crumble in just a few decades. Engineers searched for a long time for a way to make these foundations last forever, until they turned their attention to ancient port structures in the Mediterranean. It turned out that 2,000 years ago, builders used a strange mixture that did not weaken when exposed to salt, but instead became as hard as diamond. The secret of this ancient alchemy completely changed our understanding of durability. Why do modern concrete supports crumble after 50 years, while structures from antiquity stand in salt water and only grow stronger? Scientists studied the concrete used in ancient Italian ports. Inside the stone, they discovered unique crystals. Ordinary concrete simply does not contain anything like them. Modern engineers spend billions protecting structures from salt. We were only able to decode the ancient system using modern electron microscopes. The main secret was the addition of volcanic ash collected from the slopes of Mount Vesuvius.
But the real intrigue is that the ash alone did not make the concrete eternal. The magic began the moment the blocks were submerged in the sea. Salt water came into contact with the ash elements and lime, triggering an extremely rare chemical reaction. Inside the pores of the concrete, a mineral called aluminum tobermorite began to grow. Its long plate-like crystals spread throughout the entire mass of the block, binding it into a single, ultra-strong network. Imagine this. The harder the ocean pressed against such a support, and the more salt penetrated inside, the more crystals grew, sealing every microscopic crack. It was the effect of a perpetual engine. The very environment that was supposed to destroy the structure was actually continuing to build it. In today's industry, we use cement that begins to expand when it comes into contact with sea salt, eventually tearing itself apart from the inside. We fight against nature, while the Romans built it directly into their production process. Modern engineers were stunned to discover that even after 2,000 years, strengthening crystals are still growing inside ancient supports. If we used this formula today, our bridges and dams would not require repairs for centuries. But why are we still not doing it? The problem is speed. Roman concrete takes years to reach its final strength underwater, while modern construction schedules demand immediate results. But even the Roman magic of concrete becomes useless where the depth of the ocean drops into an abyss 300 meters deep and beyond. At such distances, traditional construction methods are impossible. Here, technologies come into play that look more like launching space rockets than ordinary construction work. In China, engineers have learned to assemble bridge supports like gigantic floating cities and tow them into the open sea. These are enormous hollow towers weighing hundreds of thousands of tons, which must be placed onto the seabed with perfect precision while battling underwater currents and powerful winds. Now we will see how engineers control structures the size of skyscrapers in the middle of a raging ocean, where any mistake could send a massive structure straight to the bottom. Do you think modern supercomputers completely eliminate risk when building supports in the open sea? During the massive Shenzhen-Zhongshan Bridge project, engineers faced a situation where a gigantic steel cylinder weighing hundreds of tons became jammed halfway to its target. The plan was simple. Powerful vibration systems were supposed to gently press the support structure into the seabed silt. But at a depth of 40 meters, the steel encountered an unexpected obstacle, an ultra-dense layer of ancient rock that the survey probes had mistakenly identified as ordinary sand. The cylinder began to tilt under its own weight. If the steel tower had leaned just a few more degrees, it would have jammed permanently, turning a foundation worth tens of millions of dollars into a useless pile of metal. The engineers deployed a technology known as injection softening right in the middle of the installation process. Special robots operating under pressures of several hundred atmospheres began pumping water and chemical agents into the ground beneath the jammed edge of the support. The solid rock turned into a soft slurry within seconds. It was precision work on the finest level. The ground had to be softened at the exact point where the steel had met resistance, so the structure could return to a perfectly vertical position. Laser sensors tracked every movement of the construction. Operators aboard the barge adjusted the flow of the solution, preventing the half-million-ton structure from plunging uncontrollably into the abyss. An even more dangerous incident occurred during the construction of the Hong Kong-Macau Bridge, when an installed concrete foundation began slowly and seemingly uncontrollably drifting to the side. The underwater current in the river delta turned out to be so powerful that it started washing soil out from beneath the massive slab, creating a gigantic void underneath it.
Satellite monitoring detected that the support had shifted several centimeters toward the open sea. To stop the movement, engineers began injecting cement slurry beneath the foundation under enormous pressure. The mixture instantly filled the cavities and turned the mud surrounding the support into artificial rock, permanently locking the structure into its design position. Once the foundation settles into its final position, the inner cavities of the cylinders are filled with millions of tons of sand and concrete.
This transforms the temporary steel shell into a solid artificial island that no longer depends on the unstable seabed below. On top of these foundations, engineers build pylons capable of withstanding the direct impact of a tanker weighing 300,000 tons. The support becomes part of the Earth's crust itself, carrying kilometers of roadway above the raging strait. Construction is completed with the installation of the final stress sensors, which will monitor the stability of the foundation in real time for the next 100 years.